Yes, it is. Does it work? Good lighting. All right, yeah, that's sort of a seminar. So feel free to ask plenty of questions. So I guess let me first recap real quick the orthonormal matrices. That's what orthonormal matrices led us to. So transform coding is an application of orthogonal orthonormal matrices. So let's just recap that real quickly. So if I had a matrix, which was an arbitrary rectangular matrix, m by n, actually not completely arbitrary, let's assume that m is greater or equal than n. So it's like this type of a matrix, the tall and thin one. Then we say it's orthonormal if QTQ is identity, right? So I could write it like this, Q orthonormal. Or you could say orthonormal columns. If Q happens to be square, oh yeah, here is one fact I wanted to tell you. If Q happens to be square, then the fact that Q is orthonormal implies that QT is exactly Q inverse. Because if I have a square matrix, I can talk about its inverse, right? And the inverse has the property that Q inverse Q is identity, and it's unique if it exists, right? And because we know that QT has this property, that means that the inverse, because it's unique, has to be exactly QT, right? So this is for square matrices, because for rectangular matrices, I don't have a defined inverse. There will be a pseudo inverse, which we might discuss even today, but it's a slightly different thing than inverse. Inverse is just inverse. Yeah, you see that this means really orthonormal columns, right? I want you to have this picture. If this is Q, then my transpose is QT. It looks like this, right? So what I'm doing here is I'm taking, here are the columns, right? Because columns became rows in the transpose matrix. So I'm multiplying the columns of Q with the columns of Q, right? So this really means that if okay, let me do it one more time. If I denoted the columns as Q1 to Qn, then this QTQ equals identity is just a long way of saying that for each I from 1 to n and for each j from 1 to n, the dot product QITQJ is delta ij. Do you know this delta thing? The Kronecker delta. It's a super simple thing. It's just so it's either 0 if I is different from j, and 1 when I is equal to j. This is the Kronecker delta. So this is really just like a long way of saying the same thing, right? And you should see from this picture why. Yeah, you can you can almost discuss about it. It's just a few of you, so don't be shy. Yeah, this delta thing becomes important when you have to move to higher order things. We always talk just about matrices, but you can go higher order and talk about tensors. Those would be actually like cubes of numbers, right? This is like a rectangle of number, but you can have a box of numbers, and those would be tensors, and these guys then become more important there. But we will not be covering that. I barely know it, to be honest. Oh, and what I wanted to tell you about square orthonormal matrices. So some people, when they mean orthonormal, they mean just square, but we can just talk about orthonormal matrix, which is rectangular. But if you have a square orthonormal matrix, there is one cool thing. Because, so let's assume that Q is square orthonormal. So I know that inverse is just QT, right? So Q inverse Q So that's identity, right? But you also know from group theory, the elementary group theory we were discussing, that I can also flip it, right? Because if two elements multiply to an inverse, then they actually commute. That's a special case where they do commute. But the Q inverse is just QT, right? So this is just QQT. And I can actually do it because Q is square, right? So the QT has exactly the same dimension, so I can multiply them in either way. I couldn't do it with these guys, right? I couldn't do QQT because the units would not. Oh, could I do that? Oh, I think I could, right? What would be QQT? QT would be. Yeah, I could still do that, but I wouldn't get the identity matrix. So let me finish this thing before I confuse you more than necessary. So if Q is square orthonormal, then it means that QQT is the same as QTQ. Both are identity. And what does this mean? What does mean QQT? So here we were looking at the case QTQ, right? And I said it means multiplying columns, multiplying in the sense of dot product, columns of Q, all columns of Q against all columns of Q, right? This is also what this is saying. These are the columns of Q dot producted with all columns of Q, right? And if I happen to be dot producting the column with itself, I must have 1. And if I have two different columns, I must have 0. That's what this connected delta is telling me. So the QQT is exactly the same idea, but are you paying attention? But on what? On rows as opposed to columns, right? If you think about it, so if this is my Q, this is my QT, then what does it mean? So this here I'm looking at a row, and here I'm looking at a column, but these columns are just rows of Q, right? So this is really taking dot products between all rows of Q. So this is looking at rows. So this is interesting because this tells us that if Q is square and orthonormal, it means that it has both orthonormal columns and rows. That's the special case of a square orthonormal matrix. Now if I have a rectangular orthonormal, then it clearly cannot be the case, right? I cannot have the rows to be orthonormal as well. If I have like bunch of rows here, more rows than columns, then it can't be orthonormal. Why it can't be orthonormal? Why? So if I have like m equal 20 and n equal 10, so 20 rows and 10 columns, why the rows cannot possibly be orthonormal vectors? They could clearly be units, sure, no problem with that, but they cannot be orthogonal. That's because, do you have an idea? Huh? No. All the rows, they would be all of the same size. I sort of like draw it sloppy, but all of them have 10 elements here, right? There's 20 rows, 10 elements each. Before the last lecture on Friday, we showed that if vectors are orthogonal, they must be linearly independent, right? And because these are 10-dimensional vectors, I cannot have more than 10 linearly independent vectors there, right? Because the dimension of the space is 10, so the maximum number of linearly independent vectors is 10. If I had 11, that's impossible. So these rows, they have no way of being all orthogonal. So that also means that if I do the QQT for a rectangular matrix like this, then I cannot possibly get identity, which is interesting. Okay, so this was, is it clear? Some questions on orthogonal matrices? So what follows, what I will show next, is the transform coding, which is one very cool application of orthogonal matrices. It's essentially like application in like data compression. And data means arbitrary signal. It can be used for audio data or images or even videos. So let's get to transform coding. So first of all, we need to formulate our problem in linear algebra. So we need to like translate it into the language of vectors, right? So if we have, for example, audio signal, you know that audio signal is just like just like a function, right? Which from R to R, like a continuous signal. When I recorded some audio stream, if it was stereo, I would have two of them. But the way how like microphone or these recording devices work in general, they sample this function at discrete time intervals, right? The higher frequency the sampling is, the better approximation of my signal I will get, right? So, and these values of the signal, this would be like my sound wave. These values I can just concatenate and put them into a vector, right? So like an entire sound clip, like the sounds you have on your computer when it makes like ping, that's just like one clip. And you can imagine that's just a vector. It's a sequence of numbers, right? And sequence of numbers, it's beautifully represented as a vector, right? If I have n numbers, it's an n-dimensional vector. Now, but an image would be similar. It would be a little bit trickier because image is 2D, right? So I have some image with some pixels. That's sort of closer to me. The only thing that's trickier about it is that I need to convert it to a vector. So I need to unroll all these columns into like a gigantic column vector. The point being that I can, for example, take the first column from here, put it here. Then I take the second column and put it below it. The third, and so on, right? So I just unroll it, the whole image. I can unroll the entire image into a vector, right? That's no big deal, I hope. So then I'm left with the vector. And my signal is n-dimensional vector. And of course, if I want to transmit it, I just transmit the vector as it is. But sometimes I want to apply data compression. And this transform coding is exactly like a type of lossy data compression which leverages the property of orthonormal matrices. Specifically, the property that the inverse is just transposition. And we will be using just the square orthonormal matrices here. So geometrically, the orthonormal matrix is not always a rotation, right? We were discussing that before. Orthonormal matrix can be a rotation or reflection, exactly. But here in transform coding, I think we typically design it so that Q actually is a rotation and not a reflection. Wouldn't really matter because all we need here is that it's easy to compute the inverse. It's just a transposition. And the idea of transform coding is to pick a smart Q, and that's what I will discuss next, what are smart Qs, such that after I perform this rotation, or you can also think about it as coordinates with respect to the orthonormal basis described by matrix Q, that they have the interesting property that only a few of them are large and non-zero. They like quickly drop off, and there are some like super small coefficients further down which can essentially be discarded. So the idea of the compression is to just truncate this, say this is 0, and transmit just the first few coefficients. So it's not lossless data compression. You will not get exactly the same signal as you started with. You get just an approximation. But the idea is that you get a pretty good approximation with much less memory, with much smaller n. So let's look. So the whole trick essentially is what is this basis, right? For example, if I pick the standard basis like this is a perfectly valid orthonormal matrix, right? It doesn't really do anything because it's the identity, right? So that one is not going to help us. It's not going to do any useful compression. But there are orthonormal bases. There's actually a bunch of orthonormal bases. One very popular one is called the discrete cosine transform. What is cool about the discrete cosine transform is that I don't even have to like explicitly store the matrix because I have an actual formula to compute the entries of the matrix. And if I have a formula to compute the entries of the matrix, I also have, of course, a formula to compute entries of the transpose of the matrix, the same thing, just like rotate it or just flip about the main diagonal. So I don't even need to store the matrices anywhere. I can just always compute them with the formula. So I don't want you to remember this formula by heart. I just want you to remember that the DCT is closely related to discrete Fourier transformation. What is funny about Fourier transformation is that it's in the complex domain, and we don't need this here, so we just take essentially the real component of it, which corresponds to discrete cosine transformation. And what this basis is, I can just draw it for you. So if I I don't remember exactly what is the interval. Let's assume the interval is from 0 to 1. So these functions, so these basis functions are, so I'm sampling this interval with some sampling rate. And then my signal is some function here. And these vectors q, which are just the columns of my orthonormal matrix, are also some functions on this interval, discretely sampled, right? I assume now everything is discrete here. Now you can think about this not just in the discrete case. You can also talk about the continuous version of these transformations. Continuous version is actually sort of fun. You know what dot product becomes if I have continuous functions? If I didn't say that this function here I want to keep it simple, so I'm dealing with sampled things, right? They can be sampled pretty finely. There can be like lots of samples. So like intuitively, it's almost the same thing as the continuous function, right? But mathematically, it's different, right? Because the continuous function has infinitely many variables, as opposed to this discrete sampled function, which has only finitely many variables. Do you know what is a dot product in functions? It's just the integral. If I want to do dot product between functions f and g, which are both functions from 0 to 1 to r, then the dot product f dot g is just integral of f times g. But that's the continuous. Let's forget about this continuous version. Even though I just make this note that you know that there is a continuous version of this. But let's look at the discrete version. So I have some signal, which is some sampled thing. This is my, if I sampled it, I don't know, like 10 samples, then I have 10 samples here, I have 10 values. And my basis will be 10 basis vectors. So how do they look like? And here is the main magic of this discrete cosine transform. So so I'm on interval from 0 to 1, right? And the first guy is just a constant. It's just a constant function. That will be my q1. My q2 on the interval 0 to 1, sampled with my sampling rate. Am I making sense? Cool. What do you think will be the second one? That's a good guess, but it's actually funnier than that. It's actually just like one wave of a sine curve, like this. Because here is, if you look at this formula, it's some cosine, right? With some scaling coefficient here. So this is just like one wave of a sine curve. The third one would be like two waves or something like this. Then the fourth one would be like one more oscillation, I think something like this, and so on. So this is essentially a frequency decomposition, right? Because think about it, if I take the signal y, so if I now build a matrix q1, q2, q3, q4, and so on, right? This is gonna be my matrix q. And guess what? The cool thing is that these guys are actually orthonormal. The fact that they are unit, I can always achieve that by scaling, right? And the fact that they are orthogonal, that's not so trivial. But like for example, the q1 and q2, like if I draw them together, they would do something like this. So essentially, if you multiply them together, it sort of subtracts itself, and I get 0. Sort of cool, but that's the magic of these bases, that they actually are orthonormal. And all the other ones too, right? Q2 times Q3, again, the dot product is 0. That's the really cool thing about. That's one cool thing about these bases. Then there is another one, which is that this is essentially like a frequency decomposition of my signal. So if I do, okay, allow me to do it from the left because I'm an idiot and I wrote it in columns as opposed to rows. So if I do it, the point is that I want to do dot products of my signal Y. So Y is my input signal, something I measured from the outside world. I took a picture and it's an image, or I recorded a bit of audio like I'm recording right here. So that's my Y. And I dot product it with all these vectors of the DCT basis. So the dot product is essentially like projecting the vector Y into all of these components. In other words, Y to Q1 tells me how much of a constant gain is there, right? Y to Q2 tells me how much of this wave will be there. Yeah, it's sort of like, how would I explain that? This is sort of like the geometric interpretation of the dot product, right? If I had on the input just this, just a straight line, then the first vector would be 1, because it's orthonormal, and all of the other ones would be 0, right? So the first one would get excited maximally. If my input Y is just Q2, then I get 1 only here and zeros everywhere else, right? My real signal, which I measured, is some mix of these things, right? It's some coefficient, some alpha 1 Q1 plus alpha 2 Q2 and so on, alpha 3 Q3 and so on, right? And by doing this transformation, I isolate these coefficients. So in a sense, this Y transpose Q is telling me how much of each frequency is in my signal. So it's like frequency analysis, if you will. Do you sort of see that intuitively? Cool. And this is super useful because like if I continue there, and if I had like really high frequency sampling, that like the low guys, they would be some crazy high frequencies. They would be something like this. And this is something that doesn't really happen so much in natural signals, which are usually like nice and smooth, right? If you take a picture, there are some edges and like sharp things, but like most of the areas are varying pretty smoothly. So it turns out that the first elements of this basis, they pick up most of the signal. So that means that only if I keep only first few of these alphas and say that the remaining ones are 0, I'm taking a pretty good approximation of that signal. Even more importantly, if those are real signals, there is always some error, some noise in the measurement. And the noise is usually high frequency noise. It looks something like this, right? So I could do like, if I had 100 samples, then like my final one would be something absolutely crazy. It would be something like this. And this is something I probably don't want there anyway, even if it was there, that it's just like some unwanted noise. It probably has a very, very, very small amplitude, right? So this alpha 100 would be like something like 0.0001 or something really small. So if I just make it 0, that's fine. That's, I guess, one of the justifications for like lossy image compression or something like that. But the image is not exact to begin with. It was already captured with some error. So who cares about reproducing it exactly when it was not exact to begin with? And this applies to audio, to images, to video. So for images, this is exactly what's going on in the JPEG standard, or at least in the classical JPEG image compression standard. That's exactly using this discrete cosine transformation. So the special case, the special thing about the discrete cosine transformation was that the orthonormal matrices I did not have to store anywhere. I can always compute them with my sines and cosines, which is nice because you don't need any memory. You just need compute. So the JPEG works. It takes the image and splits it into small 8x8 pixel blocks. That's why if you like dial up the compression ratio in JPEG, you might have seen it. You see like this blocky artifacts that like the blocks start to stand out. If the lossy compression is not too lossy, if it's like pretty good approximation of, it's pretty close to the original. Of course, you don't see the blocks because it just looks the same. But if you dial the compression up, you start seeing these blocks, and that's because how it works. And then the key, the heart of JPEG is that for each of these 8x8 pixel blocks, you do exactly this DCT transformation. So it's an 8x8 pixel thing, so it's a 64 dimensional vector. And on the 64 vector, we do one-dimensional discrete cosine transformation. And then there are some additional tricks how to further compress it down. But the main point being that if I have my, assume this is 8x8, this is 4x4, no, it's 8x8. So if this is my input signal, this is really like some image. I don't know, it's going to be like something. So with DCT, I convert it into another 8x8 image, which is the spectrum of that thing. And what you will see there, if you look at it, if you do this experiment, is that all the interesting stuff is concentrated somewhere around here. And here you have like funny numbers, like really small. So then the idea of JPEG is to take just this top part, there's like some sort of like zigzag ordering, and at some point it just cuts it off. And then there are some additional, there's a bunch of additional tricks how to further compress this zigzaggy sequence. But the main idea is really just to cut off this remaining portion after the DCT, discrete cosine transformation. And now to transform this back, all I need to do is the inverse transformation, back from here to there. So if I took the original thing, if I did not truncate, if I didn't zero anything, then just if this was my matrix Q and this was my matrix QT, I would get exactly back the right thing. That's because QQT is identity, right? And QQ it's identity, so it returns me back the signal I begin with. And if I zeroed out some small coefficients, I don't get exactly identity. I don't get exactly the same thing, but I get something very close to it. So in JPEG, it's slightly more complicated because it's a two-dimensional thing, right? But here the basis vectors are just outer products of the 1D DCT thing. So those are these wavy things I was showing here. You just have to do the outer product between every pair of them. Do you remember what was outer product? That's the funny case. So Qi here is a column vector. Qj is also a column vector, but Qjt will be a row vector. So this is, I was saying that before, this is the outer product of two vectors. And it turns out that this actually gives me orthonormal basis. I will not prove it here because it's easier done after I have some more tools in linear algebra, but you can believe it for now. So those are 64. This way I get 64. So I start with 8 basis vectors for 1D DCT, and I take all of their outer products, and I get 64 dimensional basis for all the 8x8 images. This gives me my matrix Q. What is the dimension of matrix Q? The Q will be 64 times 64, right? Because it takes one 64 dimensional image block and turns it into a different 64 dimension. This was 64, turns into another 64. That's fine, it's a orthonormal matrix. The nice thing is that I usually don't like represent it explicitly using numbers in the matrix, but I just know how to compute every element of that matrix using this funny cosine sine formula. So DCT is just the tip of the iceberg. There is like tons and tons of bases. Wavelets are an example of orthonormal bases. And you can study this for like an entire semester. I took one like class for a whole semester, just on wavelets. The simplest one is the Haar wavelet, which is sort of cool. So again, the idea is the same. I'm just looking for interesting orthonormal bases, which will be useful, for example, for compression. Yeah, and the wavelet bases are another. It used to be very popular some time ago, because I think you may get better compression with it than with like DCT. I think like the JPEG 2000 maybe might be using, the newer JPEGs might be using these bases. And the idea of the wavelets is that they are not just like global waves, like in the previous case. So here you might notice that these are always waves on the entire interval. Wavelets are not like this. They are always just, they are usually just like on a piece of that interval. So let me explain on the Haar wavelet, which is the simplest case. So again, I will be talking about an interval from 0 to 1. That's the simplest thing to explain it on. And the first will be again just a constant. I always need the constant there so I can reproduce a constant, obviously. And the main shape of the Haar wavelet is this. So this could be like +1 and this could be -1. This would be like around 0. So it's like one bump up, one bump down, essentially. These lines are like, you can disregard them because it's a function, right? It's a function from my interval 0, 1 to, in this case, -1, 1. And then how do you construct the remaining basis vectors? You just scale it and translate it. So watch this. So again, this is my 0 and this is my 1. So let me do like a little grid here. So the next one is I cut it in half and I scale it, and that's it. This would be my, this is Q1, this would be Q2, this would be Q3. And the next one would be the same thing except that translated to cover like the second part of that interval. Do you see that? And then then to get the next one, so if there is again my 0 to 1, I would scale it even more. So scale it to 1/4. And then the remaining ones would be just translations of the same thing, right? And then I would translate it even more. And the final one would be translated all the way down up to 1. So this is my 1. So you can see there is sort of the same idea is going on here. Like the lower I go, the finer details I can pick up, right? But unlike the DCT, the wavelets, they are localized. They are sparse, right? Because every one of them only is looking like at a small spatial neighborhood, right? If it was like on an image, that means that each wavelet, especially the ones that are like further down in the list, they're just looking at a small piece of that image and they ignore the rest. So that's called spatial localization. The very cool thing is that they are also orthonormal if you normalize them properly. The main point is that they are orthogonal. You can sort of see it from here, right? If you do dot product, if I do dot product this with identity, I just get this, and this thing subtracts with this, so I get 0. Same thing here, right? Here it's 0, so this cancels out, and this thing is just multiplied by 1, again, subtracts itself. Right? And of course, if I do dot product of these two guys, this is just 0 with 0, again, I get 0. So it's an orthonormal basis. So I don't need you to remember the details of the DCT or Haar wavelets. My point here was that those are examples of orthonormal bases, which are extremely important in applications. Wavelets are used quite a lot. And you can construct many orthonormal bases. Every one of them will have slightly different properties. And there is like a bunch of different wavelets, and people argue that ones are like slightly better for compressing this type of signals, and others are better for different types of signals. But my main point here really is that these are just special types of orthogonal bases. Any questions on this? If not, the next thing we are going to move to is projection. That's essentially, so next we want to cover least squares. And the simplest one-dimensional case of least squares is just the projection of a vector. I've actually already seen like a simpler case of this before. So maybe I can just start with an example. Or let me derive those formulas rather than just like presenting them as given. So what I want to do is I have this vector b. So this is some vector b. It goes from 0, as all good vectors do. And I want to project it onto vector a. So what that means, projected, I want to do orthogonal projection. So what that means is I want to find the vector TA, where t is some real parameter, such that if I do b minus TA, so this is b, this is TA, so b minus TA is this, I will get something that's orthogonal to a. So what does it mean orthogonal? That means that the dot product is 0, right? So this is saying that b minus TA, actually let me make sure. Dot product with t is 0. Right? Do you see what I'm doing? I'm just trying to find this t such that I find out how far on this line should I march, such that this difference between b and the vector how far I marched is perpendicular orthogonal to a. Right? I'm looking for projection of the vector b onto the direction a. The result is going to be TA, and I already know the a, that's my input. What I don't know is the t, and that's what I'm trying to compute here. So this says is that ATB has to be equal to ATA, which means that T has to be ATB divided by ATA. So the result of the projection is T times A, which is just ATB divided by ATA times A. Right? That's my projection. You can compare it to what you see on this slide. So if I'm given two vectors, just as I was demonstrating before, you have the same picture here. So the projection of B on A, and that means the orthogonal projection. So like you can imagine if this was the ground, try some radical video experiment. If this was like the ground, and this was some weight, and I like let it fall on the ground in the direction of the gravity, so perpendicular to the ground, where would it fall? It's one way you can think about it. And what I just derived, you can compare. It's the same to this formula. It's except that it doesn't fit there. ATB divided by ATA times A. Whereas another way how you could derive it from dot products, right? You said that if my vector A was unit, then the projection would be ATB, a unit A, times the unit A, right? If you remember, this is when we discussed dot products. We said that the dot product is also the dot product of B with a unit A is the length of the projection on the direction specified by the unit vector A. So this is just the length, just a scalar. So if I multiply it back by the unit vector, I get back exactly the projection. And because A with this hat is just like a unit, if my A is not unit, then I can unitize it by dividing by the length of it, right? And what this thing is just ATB divided by norm squared of A times A, but norm squared is nothing but ATA, right? So this is again just the same formula. So there are like two ways to derive this formula. Do you see that? So this is a formula for this B parallel thing. So this is the B in the direction of A. In other words, it's just the component of B in the direction of A. You sort of remember how we are talking about subspaces when I was talking about rectangle matrices. So this is just the component of B in subspace generated or spanned by the A vector. Now you can be the logical question to ask, what is the rest, right? What is the component of B perpendicular to that subspace? That's this B perpendicular sign. So that's the rest, right? If this is the part of B on the direction A, then this B perpendicular I simply get as B minus B perpendicular, right? Where here I substitute the formula from here. That's just this formula substituted there. And here I have to be a little bit careful with the algebra. If I'm looking at ATBA, I was saying that we have associativity, right, when doing matrix multiplication, but only if the dimensions agree, right? So what is going on here? So all of them are column vectors, right? It's my convention. Everything is a column vector unless otherwise specified. So those are just two column. So the T makes a column vector, row vector. B stays column vector. So this is just a scalar, right? The first thing. And this remains a column vector. So I cannot write that this would be ATBA because BA are two column vectors and their product is not defined, right? That's not a valid matrix product. Right? What I can do, however, is because ATB is just a scalar, I can say that, let me write it nice. ATBA is ATB because scalar multiplication can be done from the left or from the right, right? Doesn't matter. And now I can apply associativity because A is a column and AT is a row. So what I have here is an outer product. And that's totally fine. So I can do this. So the top here, ATBA, I converted to AATB. And that's exactly what happened in this step. So you can now see that this really is the same thing because identity times B is just B, right? And this is just AATB as opposed to ATBA. And this is why this works. It's divided by the squared norm of A by ATA, but that's the same in both, right? So in other words, this is a matrix. This is an n by n matrix, which for B returns me this orthogonal complement of B. Right? I could also take this matrix. This matrix might be even more interesting, actually. AAT divided by ATA. And this matrix is the projection matrix, which for a given direction A gives me the component of the vector projected onto the direction A. I can denote it as a projection matrix. Does everybody see that this is a matrix, a nice square n by n matrix? The funny thing is here that on the top of that, it's a funny one. Here on the top, so what is it? The denominator, numerator? I always confuse it. What is the one on the top? Numerator. So the numerator is a matrix, and the denominator is a scalar. Everybody sees that? The funny thing with this matrix is if I do p square, which is p times p, then what it is? It's 1 over ATA squared, right? That's just a number. And here I have A, AT, AAT. Now I can apply associativity, and what I get is that this is just AAT divided by ATA, because this one cancels with this 2 here. Do you read me? And it's just P. So that this matrix has a funny property that P squared is P. This is called the projection matrix. Sort of makes sense, right? If I once project the vector onto direction A, if I project it again, it must do nothing, right? Already has been projected once, right? So squaring the matrix just means applying it twice, but applying the projection twice doesn't really do anything. It's the same as applying it once. So let's summarize this. What we learned about projection matrices. So for any vector A, the vector A is fixed. That's my fixed projection direction. So this is the matrix which gives me the orthogonal complement to the direction A. Now, funny variation is if I do it twice. So the only difference between here and here is that instead of this 1 here, I put 2 here. So instead of subtracting, so let's look at this picture. Instead of subtracting this B parallel once, I subtract it twice. So what that means is that my B goes this way. Okay, I need to write it. I need to draw it again. So this is a reflection matrix. So this is my coordinate system. And I have some direction A, and I have some vector here. Then after reflection, I just flip it like here. So this would be the reflected vector. So if I start with this one, let's call it B, I get C, which is the reflection around the A-axis. By the way, this is a pure reflection. You can prove that this is an orthonormal matrix, and it's not a rotation, because it's a reflection. In these reflections, this is called the Householder transformation. They are very important because any rotation can be expressed as a composition of 2 reflections, which is sort of interesting. Anyway, I don't mean to go into too many details on this Householder business. What I want to go into, but I will not have the time to do it today, I'll do it on Wednesday, is to generalize this projection thing into projection on a subspace, which will ultimately lead us to linear least squares. This is very important and again very useful algorithm. So what I discussed so far is projection on a one-dimensional subspace, just in a direction, just on a subspace generated by one single vector. And then the following, that's what we're going to do on Wednesday, we'll generalize it to a projection on a subspace. So instead of one vector, we will have a subspace generated by a bunch of vectors, but we still want to project onto it. And that's exactly linear least squares problem. All right, any questions? I never have any questions because you want to go, but it's okay.